All right, good evening, everyone. Welcome to the Ngong Beng public lecture series, which is organized by the Institute for Mathematical Sciences. It's a great pleasure to have Kieron Burke in Singapore and delivering the lecture today. He's from the University of California, Irvine. He's a Chancellor Professor there, and he's Fellow of the American Physical Society, the Royal Society for Chemistry. It says British Royal Society on the website, but that Royal Society is implied that it's British, so. He's mostly known for density functional theory. He has made groundbreaking contributions in the 90s, and a little bit of trivia about him. He's last year he got 15,000 citations. That's what he gets now per year. And I've done the projection for this year will be around 18,000 from a Google Scholar projecting for by the end of the year. So that's, so it's currently have more than 100,000 citations. So that's just to set the bar. He's going to talk about the importance of quantum mechanics to saving our planets. Please, Kieron.
Thank you. Thank you. So it's a great pleasure and an honor to be here in Singapore and to represent our program at the Institute for Mathematical Sciences. We have many scientists and mathematicians from around the world here for really a great month here in Singapore, organized by our host, Burke Englert. And so I've been asked to sort of represent the program and tell you a little bit about what we do. But most of what I'm going to focus on is the sort of context in which we work. But there will only be 125 equations in the presentation and 10 quiz questions at the end. Okay, so pay attention. This character here will play an important role in what I'm going to talk about. And, just randomly, I'll pick a member of the audience to see if they can identify this fish. You young man in the green shirt there, what fish is that? We'll get back to that one. Okay, so the themes are... I'm going to talk just a very little bit about global warming and simulation and theory. Going slow. Quantum chemistry and why it is hard. So quantum chemistry is a branch of chemistry where we try to simulate reactions on a computer. Then I'm going to talk a little bit about density functional theory, which is a way of doing quantum chemistry that makes it run much faster, but also brings in lots of approximations. I'll talk a little bit about applications, and then I'll talk about what we've been doing for the last month at IMS. Okay. So basic facts of climate change. So one thing I'm very fortunate about is this theory that I work on is used in almost all branches of science. And so I get to visit many different departments, and I make friends in all sorts of places. But I teach chemistry to undergraduates, and one thing I teach a bit about is climate change. And I started doing this course about 10 years ago, and it's very interesting and also rather frightening when you look at the state of the planet, even when I started 10 years ago, and what you see in the news today. So basic facts are the CO2 has increased in our atmosphere quite a lot during the Industrial Revolution. The mean temperature of the planet has gone up by at least 1 degree Celsius. Extreme weather events are rapidly increasing. When I started teaching that course 10 years ago, scientists would not state definitively in public that extreme events would increase, and now it's basically taken for granted. Aerosols are really, really important in modeling the atmosphere. One crucial thing is clouds. We do not know if clouds help cool the planet or heat it up. And that's because the little particles that that are seated in the clouds are very, very complex chemistry happens in these little aerosols. So the details of the chemistry are very important, and a big part of modern climate science is running huge atmospheric models with huge uncertainties, and some of the world's largest supercomputers have been developed in order to run these codes. And the models show that the heating of the planet is directly related to the CO2. You can run the models with and without the CO2 output from humanity, and so it makes it very clear what the cause and effects are. Okay, and this is a very, sadly, low resolution, very famous curve called the Keeling Curve. And this is the amount of CO2 in the atmosphere for the last 60 years, and it's measured on a mountain in Hawaii, so the air is very clear and you're not close to the sources of CO2. And here you definitively see this increase in the amount of CO2 in the atmosphere. And in another, 30 or 40 years, we will have effectively doubled the amount of carbon dioxide in our atmosphere during the Industrial Revolution. Nobody argues about how much CO2 there is in the atmosphere. People argue about its consequences. Okay, so now I'm going to talk about simulations of materials. And so what we do is we solve, the simplest way of doing a simulation is to solve Newton's equations, the classical equations for the atoms at a given temperature and pressure. And to do that, you have simple forces very often between atoms. And people have learned how to make these force fields. And you can do 1 million atoms for many picoseconds in such a simulation, and they're very common in biology and biochemistry. And, these little dots are water molecules, and you have some huge biological system, and you can learn a lot about biochemistry doing that. But these simulations more or less cannot break bonds. When atoms, as we'll see, when atoms come together to form bonds, the energy to make and break bonds can't be simulated by those kinds of force fields. So that's where the quantum mechanics comes in. And so this is a picture from the early days of quantum mechanics. And these are the famous physicists who helped develop quantum mechanics between about 1900 and 1930 or so. And the real thing, so this is a sort of cartoon guide that I use in my course to explain these things. The most important thing you learn from this picture here is that in order to develop quantum mechanics, you must have a really bad haircut, right? And I was very fortunate. I spent the last 5 months in Bristol, in England, where Dirac had been a student. And see, here's a picture of him, and he really does have, well, that would be a mohawk in modern standards, right? And he was a very strange person, very famous physicist. He shared the Nobel Prize with Schrödinger for developing quantum mechanics. And he famously said this thing, that the laws, so once they understood quantum mechanics, that the whole mathematical theory, a large part of physics and all of chemistry are completely known, and there's only this slight difficulty that you have to solve the exact equations. It's too complicated to solve. And people would quote this in quantum chemistry when I was young, and they would be, it seemed to be a physicist saying, well, there's just this little technical problem, right? But who cares, right? We figured everything out. But if you actually read the paper from 1929, he says, the next sentence is that it becomes important to find approximate methods so that we can understand systems, right? So he knew right from the very get-go that you would need to do more than just have the equations of quantum mechanics, but you would need to find good ways of solving them. So his meaning was exactly the reverse of what people were implying. So when I first started in this density functional theory field, this was the first slide that I made. And back in those days, we made them with pens and paper. And the point of this slide is all these different parts of matter are just nuclei held together by electrons. And the electrons in all these different types of matter are all the same, right? You can't tell one electron from another. And back in those days, we had clusters. They hadn't even discovered buckyballs at that time. Okay, so the basic issue is, can you simulate chemistry on a computer? And we talk about doing it what we call ab initio, or from first principles, meaning that we're just going to start from the Schrödinger equation for the electrons. We don't have to do it for the nuclei, the protons, say in H2, because they're heavy, and they basically obey the laws of classical physics. But we do need to solve for the lowest energy state of the electrons, because they're light, they're very quantum mechanical. And if we can get the lowest energy state, we can calculate a curve like this for something like H2. So this is the binding energy as a function of the separation. So on the computer, I can choose how far apart my hydrogen atoms are. And if I know how to solve the equations of quantum mechanics, I can calculate this curve. And if I can get this curve, the place where it's at its lowest, the minimum, tells me what the equilibrium bond length of H2 is. If I look at the well depth, it tells me how much energy I need to pull it apart. And if I look at how its curvature, it even tells me how it vibrates. So all these properties of a little molecule I can get by just solving quantum mechanics. I need a computer. I can't do this by hand. But now, and for H2, nobody's going to get too excited these days, because people figured out how to do this in 1968. Okay? But even when they did that, it wasn't that interesting, because experimentalists already knew all the properties of H2, right? Of hydrogen gas. What's important is, can you do this for bigger systems that practical chemists and material scientists care about? So why is it so evil, right? So you really need to do the quantum mechanics. It's what we call a many-body problem. Every electron sees every other one, as well as the attraction to the nuclei. It's electrostatic forces. It's just attraction to the nuclei and repulsion among the electrons, but the electrons are quantum mechanical. This is a big part of the problem. Chemical accuracy. So this is the idea of how accurate you need to do the calculation to be able to predict chemistry. It's about 1 part in 10 million for the electronic energy of 500 atoms. So this is a really, really high standard for how accurately you do this calculation. And the idea behind this ab initio quantum chemistry was so we have developed methods over the last 5 or 6 decades to do this, and we can do it, and we can do it very accurately, but we say that they scale very badly. The cost of the calculation behaves very badly, and in fact it goes like the number of electrons to the 7th power. So if I double the size of the system, the cost goes up by a factor of 128. Now, it doesn't matter, with a method like that, it doesn't matter how complicated a molecule you manage to do on your world's greatest supercomputer. I can guarantee that as soon as you show it to a chemist, they will say, well, what happens when 2 of them come together, right? And then you're going to have to wait until there's a supercomputer that's 100 times better than the one that you have. So it doesn't really matter how good your computer is, you're going to run out of computer power. Okay, now, so hands up the number of people who know what a Hamiltonian is. Hands up the people who don't. Okay, so we're not going to spend too long on the Hamiltonian here, right? This is the technical stuff behind this. So behind quantum mechanics, you write down the Hamiltonian is what we call an operator for the energy of the system. and it has kinetic energy, electron-electron repulsion, that's just a classical electrostatic repulsion, and then the only difference between one system and another is which nuclei you have, the attraction to the nuclei. And what makes it such a hard problem is that the Schrödinger equation is a differential equation in 3n coordinates. So if n is the number of electrons, it's 3n. So if I have a system with 1,000 electrons in it, it's a 3,000 dimensional differential equation. So generally speaking, it is very hard to solve such an object. And the basic laws of quantum mechanics, they solve this differential equation, or there's also something called the variational principle, which says you can get the energy by minimizing overall possible wave function. Okay. So then we're going to have the greatest free lunch ever. Actually, the greatest cheap lunch ever I've had has been here in Singapore, right? The food is fantastic, right? Especially at the hawker market. So Holmberg and Combe in 1964, so that's more than 50 years ago, they proved a theorem which said that there is a sort of way around this, that if you just looked at the density, which is the probability density of electrons in one of these systems, that information by itself is enough to characterize the system, and you could do the whole calculation without ever calculating Schrödinger's wave function, without solving that differential equation. That was one step, and the second step was in 65, Walter Cohn with Lou Sham said, imagine you could just, so this is like a math trick. You just imagine in your system that the electrons do not repel each other. They are still what we call fermions. They're still quantum mechanical objects, but they don't repel each other. And in this fake system of non-interacting electrons, you could do the calculation, and if the electrons don't repel each other, it's much, much simpler. It simplifies the differential equation enormously because the position of one electron does not have an effect on any of the others. So this is a bit of a trick. This is the electronic density of a helium atom, the simplest case, 2 electrons. This is the potential, which gives you the force that the 2 electrons feel, and this red line is something we call a Cohn-Sham potential. So this is a fake, this is for 2 fake electrons that don't repel each other, and if I put those 2 fake electrons in this red potential, I get exactly the right density, and I can also extract the right energy. And so there are 2 steps. One is we can get everything from the density, and then in the second step, they define the set of equations that you could solve, and if you only knew this little piece of the energy, you could solve this set of fake equations for fake electrons, but it's defined mathematically. It will give you the exact energy of the real electrons and the real density. And this is just like made up, right? This is just a mathematical fiction, but what it turned out to be the case was it's not so hard to write approximations for this guy. So yeah, to get an idea about this, so when I'm teaching physics, there are these great simulations that you can get from a website in Colorado, PHET, and they're used in high schools and in college. And so one that they have is of explaining gravity. This is the sun, and I use it, so the Earth is going around the sun, and the moon is going around the Earth, right? And actually in this simulation, the orbit is really simple. It's just circles. But the circles of the moon going around the Earth, and actually, can I get it up here? Let me see. It's much better if we can see it. Oh, here we go. Okay. So I'm going to, with my godlike powers, I'm going to slow down the motion of the Earth around. So there's the moon going around the Earth, then you see it's just doing sort of circles around the Earth, and the Earth is going around the Sun, right? So, but who knew that if you actually plot out the orbit of the Moon relative to the Sun, and this is not to scale, right? That's the actual trajectory that the Moon makes, right? And that's actually a little bit, if we leave it running a little bit longer, we see that, you know, because the period isn't quite the same, it doesn't quite repeat itself. Okay, so imagine if you looked at this thing, but you couldn't see the Earth. Imagine all you could see was this pink line, right? Well, that's, you know, you solve the equations for the Earth going around the Moon, and that's pretty simple. And the Earth going around the Sun, and the Moon going around the Earth. And those two equations together give you this pink line. But if you couldn't see the Earth, or let's say, right, you can't afford to solve the equation for the Earth, you could imagine this pink line as coming from some sort of gravitational force in the Sun that changes a little bit with time. It gets a little weaker and a little stronger to produce exactly this pink line, right? And if you knew that fake force, then you would be able to predict the pink line without ever having to solve the equation for the Earth. So we think about, let's say, even a heavy atom like uranium, 92, has 92 electrons, right? And you cannot afford even to do that calculation very, very accurately. There are too many electrons. But what you could do is imagine some average force field on all those electrons that is fake, but that is defined so that it gives you certain properties of the electrons overall. And if you knew the exact one, you would get the exact properties. But much more importantly, you might be able to approximate. If you knew enough information about this fake force field, maybe you could approximate it well enough to get you the accuracy that you need. But if you knew that one force field, you don't have to solve for all the particles at all. You just solve one equation. Okay. Did you get that? Okay. Good. Back to neither do I. Okay, so the problem is there's this little piece of the formula that we don't know, this exchange correlation energy. And we keep trying to write down approximations for it, and they do get better over time, but they're still approximations. So here's my picture. Well, so over the decades, we have come up with better and better approximations, but they're still not chemically accurate, and they're not very reliable. They make errors that we don't anticipate, and they don't work for all the elements in the periodic table. But we would like to know this formula much more accurately than we do now. And I think, yes. So here's a picture taken from a modern density functional theory conference, right? And so some of you may remember the movie involved here and the ring, the one ring that binds them all. So this ring is sort of like this formula. So we're told from the mathematics that this formula exists, that such a formula is possible in principle, but in practice we're only able to write down fairly crude approximations. The great thing is, if you have an approximation for this formula, you get to solve these quantum equations for the electrons, but it fakes the interaction between any pair of electrons. So the cost of the calculation is much lower than really solving the Schrödinger equation. And the only thing that really comes out is the energy, but that's really the only thing that you need. And this whole scheme, this is Walter Cohn, who passed away a few years ago. And you see that big grin on his face because he set up this scheme where we hunt this functional that he developed forever and ever. But, you know, we don't know what the formula is. And this was from a school, if anybody wants to learn more of the theory, that we had about a year ago in Lausanne, in Switzerland. And we were lucky enough, so these were some of the people who developed the theory. These are chemists, these are physicists, and we were lucky enough to get two of them in our program, Wai-Tao Yang, and Mel Levy was a distinguished visiting lecturer who had to leave over the weekend. But you can get the video off YouTube if you're really into this kind of thing. Right? So these calculations have these formulas in them, and they're not always reliable, right? So there's no simple rule. So how many people here have actually run a density functional calculation? Raise your hand. You can admit it, it's okay, you're among friends. So when I give a talk in a chemistry department, almost everybody raises their hand. So when I was a graduate student, very, very few people would touch theoretical chemistry. Now most practical chemists run density functional calculations. So it's changed the field completely. So there's no simple rule for reliability. There's no way to systematically improve your result. If it turns out the approximation doesn't capture the property you want, you don't know what to do. It is completely disconnected from all other methods in theoretical physics. It's full of acronyms and all sorts of insider jargon. There are too many functionals to choose from, too many approximations, and it can only be learned from a DFT guru, right? So these are things that anyone who raised their hand knows exactly what I'm talking about, right? You run the calculation and you don't know how good it is. And now this is a list of things that the developers of the field love about, oh, I must have got my two lists mixed up, right? So as long as people have all these problems, right, I'll still have a job. Okay, and this is alphabet soup. Many of the mathematicians complain about all these acronyms. These are all the different approximations that are available in these codes all over the world. Okay, so applications. So I told you a little bit about how this theory works. And now I want to explain a bit better why it matters, right? So over the decades, things have always been getting better for theory, right? When I was a kid, people really had not been able to use the approximations were too inaccurate to make real predictions, but that's all changed. In chemistry, a very famous one is the Haber-Bosch process. So that's the process by which we take the nitrogen out of the air and make ammonia for fertilizer. So it's the largest man-made process, intentionally man-made process on the planet, industrial one, and it helped stabilize China, for example, in the 60s by being able to feed itself using this. And for 100 years, people tried to find a better catalyst than platinum for this. And a friend of mine found one running these calculations and found a combination of 4 metals using a genetic algorithm, found this combination which was better than platinum. And the company that makes all the fertilizer by this process tested his new thing, and it was better than platinum. Unfortunately, he hadn't factored in the cost of the new catalyst, which was $3,000 per ounce. So it was a lot more expensive than platinum, and so they don't actually use it. But these guys have since patented half a dozen important new catalytic reactions, all just taken from the computer. All sorts of materials design is going on this way. The world's hottest superconductor is hydrogen sulfide and was predicted by a group in China and then made by a group in Germany a year later, and it was the hottest superconductor in the world until earlier this year, when using the same methods, a whole bunch of different people have found lanthanum hydride clathrate, which is if you go to Antarctica with this clathrate material, it goes superconducting. It's minus 23 degrees Celsius. So we're almost at room temperature. The slight problem is you have to have about 1 million times atmospheric pressure to make it happen. And yes, so when they made the Airbook, Intel had to make the chips about half the size they were. Steve Jobs knew what he was doing. He said, I need the chips half the size. Intel didn't know how to do it. They did DFT calculations on material modeling, and in the process they made it half size, and they also got rid of lead from the process. Now, nobody ever got lead poisoning by licking their laptop, but if you're in the facility making these things, it really matters that there's no more lead in here. Okay, yeah, these are the latest high temperature superconductors. This is a calculation from some friends in chemistry in Bristol that I was working with over the summer. And they do, so this is a reaction barrier, right? So the barrier in a chemical reaction is between the reactants and the products. So this is really important in organic chemistry. So you find the lowest energy pathway from your reactants to the products. This determines how fast the reaction goes. If you make a mistake of a tiny amount, 1 kilocalorie per mole, it makes a factor of 5 difference in the reaction rate. So this is a disaster if you're trying to figure out how the drug gets into your blood. So here they do a bunch of DFT calculations with all those different functionals, and they get a whole range of reaction barriers. Here I have it blown up. See this soup here of different approximations. Very different barriers. And what these guys very cleverly did was they figured out how to pull out from the inside of the calculation the bit where they're calculating the barrier with DFT, and then they go back and they use regular ab initio quantum chemistry solving Schrodinger's equation for the barrier, and then they get the same answer no matter what the functional they use for the rest of the calculation. Well, why do they have to do this? It's because they can't afford to do this. They can't afford to do the full Schrodinger equation on the whole system because it's too big, right? Warm dense matter is another area I get to work in, which is all about looking at matter under extreme conditions, like in the interiors of planets. And it turns out the same theorems apply, even at finite temperatures. Okay. So interestingly, there's a little satellite going around Jupiter. It gets close every 57 days. It measures the gravity of Jupiter, which is important because we want to understand how the planet works. And there are various theories about what's going on inside with methane and hydrogen. And the different functionals give you different answers depending on which one you use. So again, these guys say, although formally it's exact, they get very different answers depending on which functional they use. So that's a real problem. And of course, you can't do experiments, or it's very expensive to do experiments at those kind of conditions. This is one of my favorites, density functional fluctuation theory of crowds. If you take the temperature very high, in fact, things behave classically, and you can apply it to classical fluids. And this is from this paper. They're actually looking at crowds of people, and they're modeling them with density functional theory. And in particular, there's an experiment of walking flies. And it's amazing because these crowds of flies, and in some cases crowds of people, satisfy the equations of density functional theory. Okay. So, to give you an idea, right, of how important this is, NVIDIA estimates that 1/6 of the world's supercomputer power is running these DFT calculations. So this is papers published, and now I estimated this one is over 40,000 a year at this point. This is an enormous enterprise, right? This is a huge enterprise all over the world. All governments all over the world are investing very heavily in this because it is essentially the way of the future for materials design and drug design, right? It is almost never a bad idea to be able to do something on a computer before you go into the lab. It's always almost infinitely cheaper. So yeah, this is in every branch of science now. Okay, so now we get to the last bit, which is what this bunch of characters have been doing. And actually there's Waitao Yang and Mel Levy. This was from, I think, our second week at the workshop. And we have this mixture of math people, mathematical physics, and physicists and chemists. But we don't allow statisticians. Okay, so what I did was I took the program and I fed it to make one of these, what we call word clouds, right? And you can, it's really good. It tells you what really been going on at this workshop, right? So most of the time we just think about coffee, right? You see the biggest one, coffee break, right? We do look at the electronic density apparently, and we have some discussions and functionals and things like that. But you see sort of what the words that go on here: dynamical, mean field theory. Jersey, are you here? Jersey's not here. He's not here. Well, tell him he was named pretty big here. Okay, so we have all these discussions. We try to tackle this problem. And in a certain sense, if you think about the whole enterprise, what comes out at the end ultimately are understanding, right? A lot of us care most about understanding, but ultimately the reason people are willing to pay our airfare and things like that is because maybe we get better approximations and they can have an enormous effect, right? Okay, so difficulties with this research. It is really multidisciplinary in a very deep way. So you get all these sort of funding agencies that want scientists to come together from different disciplines. But they usually want them to get together and produce an answer very quickly. Whereas the difficulties that we face are very deep and take often much longer. It takes us decades to make improvements in these approximations. It's not revolutionary. We've been doing this for 50 or 60 years, right? So it isn't the latest, hottest thing on the block, right? It isn't a quantum computer. It isn't machine learning, although, mind you, some of us have used machine learning methods to try to find this thing. So it doesn't sound very, it's a sort of saturated topic. It's old-fashioned, right? But the implications of progress are vast, right? It is really important. So physicists like to go on about sort of quantum mechanics and the physics of the 20th century. And they'll talk about nuclear physics, and they'll talk about astrophysics and black holes and all those really exciting things, right? In your imagination. The most important thing that physics did in the 20th century was quantum mechanics. The most important in terms of its human implications, because it allowed us to understand chemistry and understand materials. So how often is it the case that making some math progress can have overnight applications in science, right? You come up with a better formula, all the machinery is already there, right? Well, if you have a better formula, I've had the case where we've made a functional. I told it to my friend who will remain an unnamed German professor. The German professor doesn't believe me that this thing is better, but the students over here, that night, they break into the code, literally, and they change the things, the parameters in the functional, and they run the calculation. It was for gold nanoclusters. and they had better results in the morning to show the professor, who said, okay, maybe we'll try this thing, right? So that can happen overnight, right? Okay, let's skip this bit. I'm getting short. Okay, one quick example, I guess 4 minutes. So this is from my periodic table. So because I teach first year chemistry, I know that there's actually structure as you go across rows of the periodic table. This is the ionization energy, how much energy it costs to take an electron out of an atom. And all first year chemistry students learn this, that it goes down as you go along. As you go down a column, here are the noble gases. It takes the most energy to get an electron out. And here are the alkali metals, and it takes the least energy. So there's this gradual decay in this ionization energy. And we were discussing this last week. So with a very gifted postdoc, we took the periodic table and we imagined extending it for up to 3,000 electrons. But we turn relativity off because we're theorists and we can. And what we find is that this periodic structure, as you go across a row of the periodic table, actually persists basically to infinity. That you keep getting structure in the ionization energy for this last electron. Now, we did a very demanding, sophisticated computer simulation in order to be able to calculate this and extrapolate it basically to infinity to get these numbers here. And this green line is the average as we go across, say, the periodic table, the average of these numbers. And this green line is about 3.1 electron volts. And truly incredibly, our host here wrote a book about 30 years ago in which he calculated with a pencil and paper, essentially, what that number is from very simple principles of mathematics. And it's only whatever 30 years later that we're able to calculate it, and it lands almost exactly right on top of that number. And this is because there is this sort of unifying theory of this density functional theory type, where even with a pencil and paper, a gifted person can see that, and it turned out to be exactly true. And the fact that it's true, to me, is still like totally amazing, how that, no quantum chemist would have been able to predict that. Okay. So this, let me finish off. Here's one of these very large atmospheric chemistry models, right, called MECHA in this case. And so you take the kinetics of all these different species in order to, and they take, if you go through this paper, they take data from field studies from everywhere, from labs, trying to construct this model for calculating the chemistry of the atmosphere. This is in some ways the biggest unknown in all these atmospheric models. This is from, again, some friends at Bristol in chemistry, and here they have reaction rates for certain very important intermediates in these chemical reactions, and see they're using them there. So some of the time they're measuring them, but then a lot of the time they've started running DFT calculations of these things. So this is just beginning in the last couple of years that people are trying to do this, take inputs from DFT for these atmospheric models and see that they're measuring also, they're making a model of some of these gases all over the planet. And this, see this XXXXX, that means this appeared August 19th, I think. So this is what is happening, last month, right? People are constructing these models, and they're running DFT calculations to get the reaction rates for these models. But I'm telling you, almost none of our functionals are really accurate enough to get at the level that these guys need in order to make good enough predictions. They'll use them because they're good enough. And look, here again we see these reaction barriers and these complexes and things, and the tiny differences in energies that you need And you need to get these tiny differences just right so the reaction rates are good enough so that they're fed into the models of the aerosols, which determine how good our models of the atmosphere are and the effect of global warming. Okay. Oh, yeah. Rats. I gave the name of the fish, right? So it wasn't, that isn't a snapper, is it, Chris? Too bad. Okay. So what's the importance of the fish, right? So usually when I'm teaching my course with the climate change, I have a polar bear, right? And I say, you know, you want to see a polar bear in the wild, actually. You may not want to see a polar bear in the wild. But if you do, you better do it soon, right? Because their environment is going to disappear. So the gilt-head sea bream, this was a paper that I came across just a few weeks ago, and it's talking about the fish's environment near a coral reef, and what happens when when CO2 is dissolved in the water, the very, very slight change in the pH, right? Now, people have studied this for quite a while, and they think, oh, well, this change in the pH in the water isn't a big deal. It turns out a big effect is in the behavior of the fish, because they use the smell, and smell is very impacted. And they use smell to figure out where predators are. And it is very sensitive to the pH of the water. And how do they figure out? So this is all about, you know, farms of sea bream and all sorts of experiments, right? But in the middle of the paper, well, what do you know? Quantum chemical calculations, where they look, you know, with and without the proton attached to one of these olfactory molecules. They're calculating the energy difference to see if it makes sense what's going on, and it turns out it does. So all of this technology is just beginning to be used in atmospheric modeling. And so I'm going to finish. So maybe we can, right? What do I mean, right? So if you can make one of these functionals much more accurate and reliable, we could do much bigger simulations even than the ones we do today. And that would make them much more realistic and more useful. At the moment, even with our density functional methods, we still can only do about 1,000 atoms. If we could solve one of the problems, we could do 1,000,000. If we could make this exchange correlation energy much more accurate and reliable, then we would have numbers that we could really believe to go into these atmospheric simulations. And can we do this I reckon we have about 10 years. I think people are going to start geoengineering within about 10 years. If you actually look at the trends that are going on, so we don't have 100, we don't have our usual 1 or 2 or 3 decades that we take to make progress. But there's nothing that says that this is impossible. Maybe we must, right? So people at so where's my little picture? See here? Here's Gollum again, right? So I made this picture originally as a joke. But you can imagine going back in time. And you imagine if in the 60s they had the approximations that we have today. Chemistry and material science would be different now. We would be, you know, substantially more advanced because we would have understood them 10 or 20 years earlier, just by having that increase in accuracy. There's nothing that says that, you know, 20 or 50 years from now, we won't have formulas that have a factor of 10 higher accuracy. But it would be much, much better if we had them today and not 50 years in the future, for very, very many, very practical reasons. So summary, this is what I've told you. DFT is a way of doing this. Thank you for your attention.
Okay. All right. Thanks, Kieron, for the very interesting talk. Any questions? Yes. Maybe, yeah. I have a portable one here if you want one. Let me see.
Thank you for a nice talk. You've said that now essentially all chemistry students do DFT calculations by themselves, right, these days?
I didn't say they do it by them. I say chemists. So in the old days, you would need to go to a specialist to help you run the code and stuff like that. Nowadays in chemistry, you can just buy a code, and yes, you can run it. And we teach even, first year undergraduate sometimes how to start running these codes. But you shouldn't do it entirely by yourself, right? You should get a little teaching.
Yeah, but so what do you think will be the trends? Will groups specialized on applications of DFT to practical problems, will they survive, or will they gradually be replaced by just general researchers, general chemists running DFT simulations by themselves?
So actually, I was interviewed by CNN News about this about a week ago. Or no, a couple of weeks ago, and it appeared in last week's edition. And so if I'm understanding the question, those guys were asking, well, if I have NMR, nuclear magnetic resonance in chemistry, I have a facility and I have a sample, I give it to them and they do the measurement. Are you asking that, will it become this outsourced thing, doing the DFT calculations?
Will it be done by specialists, or will just every chemist simulations by themselves?
So in chemistry, an awful lot of simulations are being run by experimental groups. So at UC Irvine, we have a modeling facility, and what we do is we try to train at least one graduate student in each group in the methods, and then they teach the other students how to use it. But we like to try to train one person to understand well what is going on, because you can absolutely misuse these calculations. And they're still sufficiently sophisticated that you really need to have some understanding of what's going on inside. So it doesn't become totally sort of black box. But it is, I mean, these are groups that are totally synthetic groups. They have no background in theory. But usually you find that the students are very interested in learning how to do this because it's very important for their future.
Any other questions? Yes.
You mentioned about crowds. How about economic? Sorry, yeah. You mentioned about crowds. How about applying it to economics? Does it work?
I don't know of any case where that has been done yet. I have been to some meetings where on sort of machine learning methods and been discussing things with economists, but I don't think anyone has tried to formulate some of the economics problems in terms of density functions. It might be worth looking at, I would think, yeah. But you have to set up the equations so that these kind of tricks work. They work for liquids. So they work at finite temperatures using statistical mechanics for classical particles, and instead of doing a full molecular dynamics simulation of a liquid, you can run a DFT calculation, and the accuracy depends on how good your functional is. Yeah. So it might be possible. Yeah. I don't know.
So just a quick question about, related to that one, about this application to, what was it, sociology or what?
Well, crowds.
Crowd. So what is the basic idea? You have agents that like interact with each other, and you're trying to approximate that interaction, which is probably difficult to model by this fake force field that you're saying. And is that the basic idea?
It's a little different because it's using the sort of classical theory. So I think it's more, so crowds under conditions that are sort of analogous to statistical mechanics of liquids. So if there's some sort of you have some sort of crowd, and how they move if you sort of restrict the space that they're in, things like that. So there's an average behavior, and you can use this average idea and figure out equations for how they'll behave. But usually not in response to like one little agent, but some more global kind of effect on the crowd. Okay. It tends to give you these average results rather than the details.
Okay. Yes.
So,
all right. Yes, up there
I have
first.
the mic. So you showed one slide where you explained that the DFT calculations are used for forecasting weather or cloud motion or something. There was a map with a globe. The total showed the globe. My question is, I suppose the actual equations they solve there are of fluid dynamical type. And could you be a bit more explicit how DFT enters in the equation? I mean, are terms then modeled by DFT, or what, how does it enter? They will not solve it on a molecular level, I suppose.
Absolutely not, right? So you have global models which tend to cut up the planet into, a grid over, say, the surface of the Earth. And then you also have slices vertically, right? And then you have many different sort of variables that are all going to be coarse-grained simulated this way. But it's going to be some sort of hydrodynamics thing, right? But then in amongst that, you will have different sort of objects, sort of, say, like clouds, right? And the properties of the clouds that you need to put into the model, you get from, at the moment, kinetics studies that are either done in a lab or out in the field, and it turns out, of course, they can be very, very different. The behavior of these particles, the sizes that they grow to, and a lot of modeling is done especially near the surface of the Earth with actual emissions from cars, and it's all these volatile organic compounds. And how much you have is really, really important. And they also interact with trees and all sorts of plant life as well. So it's very, very complicated. So what the basic input that people use in the models of these guys is reaction kinetics. And the reaction kinetics you can get from calculating this barrier between reactants and products. And that's the one that you have to get really, really accurately to get a decent reaction rate. So it's this multiscale modeling where they're beginning to use truly molecular calculations to calculate the rates. The rates go into the sort of global and then up to the atmosphere.
Yes, one more question there.
Could you say something about your confidence that machine learning can help you get to better DFT formulas?
It's tricky. Maybe I can say so. So the machine learning that we currently have tends to be a sort of all-purpose tool. And the thing that it doesn't capture at all is this sort of implicit knowledge that all the scientists have and the mathematicians have about how quantum mechanics behaves. So in many cases, we can make a model, a machine learned model, that does things that none of these human-designed functionals have ever been able to do. But the models don't necessarily generalize very well. So lots of people trying to do this have the problem that when they go from one species to another, what they learned on one does not transfer. Or the other thing is even if you've just one element, that the element, when it's coordinated differently, like if you're doing crack propagation in a material, again, you sort of have these holes, these places where the machine hasn't learned enough. You give it data, but you didn't give it data there, and it extrapolates very badly. And if you're doing a molecular dynamics simulation with a force field that's been found this way, what happens is you have to run it for, picoseconds, which is many, many time slices, to see what's going on. Somewhere along the way, the system will probe a direction in which it hasn't been trained, and it goes down to it crashes, right? And so the sort of people know much, much better than machines what makes sense and what doesn't. And when we build our human-made intuitive models, even if these approximations are not that good, they tend to be sensible. And it turns out the implicit knowledge that we have about how quantum mechanics behaves, how nature behaves, it's very, very hard to teach a computer those things. So I'm not sure, right? We try it because if it could work, even if we don't really like it, even if it offends our egos, right? And we ourselves don't understand what it's doing. If it helps with this problem, I'll do it. Right? I don't care. It's that important, right?
Okay, so let's. One more question. Yes, sorry. Yes.
A very interesting talk, Prof. Thank you very much. I was wondering how to minimize the errors, because density functional theory, I used density functional approximation before.
Yes.
Because you use LDA.
Yes.
So, and we use a lot of things that you have mentioned in quantum mechanics and material and devices, like nano devices.
Yes.
So could you elaborate a little bit how to do a corrected density functional theory approximation or technique?
Yes. So are you specifically talking about my work on this density-corrected density function?
Yes, please. Yes.
So the basic principle there is when we write down an approximation for the energy, we also use it in the self-consistent calculations to calculate the electron density. In most density functional calculations, that electron density is extremely accurate. Even with the simplest approximation like the local density approximation, for most systems, it will be very, very good. But for some difficult systems, and especially, for example, anions, systems with extra electrons, it turns out that the self-consistent cycle goes wrong, and it goes wrong rather badly. And it turns out the density in that calculation is highly inaccurate. And then you turn to a much simpler procedure of quantum chemists called Hartree-Fock. And for various very deep theoretical reasons, the density in the Hartree-Fock calculation, in the cases where the approximate DFT calculation has gone wrong, turns out to usually be much better. And so what you do, and you can do it in like a couple of lines from any code, you can run the calculation, the Hartree-Fock calculation, calculate its self-consistent density, and at the very end, the very last step, you have the Hartree-Fock density and you use it as an input to a density functional calculation. And it turns out when you do that, the errors are much, much smaller than the self-consistent DFT calculation. So it's only in these cases, and we have in some of the papers written down very clear procedures for identifying when you have such an error, and then even there are scripts on the web for whatever code you're using, how to do this procedure And usually it gives you much better answers for these special situations. Does that help?
Okay, we have a small token of appreciation from IMS. Maybe you can have a small picture.
Oh. Thank you.
All right, so thanks again for the interesting talk and for the many questions. It seems to have engaged everyone quite a bit. And so thanks for coming, and thanks again, Kieron, for the interesting presentation.
Thank you. Thank you.